Hi class, welcome again to another session on digital principles and system design. So now that we have discussed basic ring counter, let us move on to discussing the twisted ring counter, also called as a Johnson counter. So this counter can be built using a seesaw shift register by providing a feedback from the inverted output of the last D flip-flop to the last flip-flop to the D input of the first flip-flop. So in ordinary ring counter, the Q of the last flip-flop was connected to the D of the first flip-flop. So in order to convert that into a Johnson counter, what we have to do is connect the Q dash of the last flip-flop to the D of the first flip-flop. Now, how does this feedback mechanism produces a unique sequence of states, and therefore this is called as twisted ring counter. So this is how we would connect the circuit if we were using a D flip-flop. So the Q dash, Q4 dash, that is the last flip-flop's Q dash, is fed back to D1. If you're using JK, then your connection slightly varies. So Q4 is connected to K1 and Q-4 is connected to J1. So let us see how this connection results in a unique change. So initially you have 0, 0, 0, 0 as the first state. Then after clock pulse 1 appears in Q1 and all others are 0. So the next is again 1 appears in Q1 and 1 appears in Q2. How does this happen? It's because initially we're just assuming that all states are 0. So Q4, sorry, I don't need a highlighter, I need a pen, don't I? Yeah. So Q4 would be initially 0. Q4 is 0, so Q-4 would be 1. So this 1 gets fed to D1 after the second clock pulse. So already if D1 is 1, then this D1 is getting transmitted to D2 and 1, as long as Q4 doesn't change, this 1 is going to remain the input for D1. So again in the next sequence, D1, D2, D3 will all be 1, D4 will be 0. So after in the next sequence, D1, D2, D3 and D4 will be 1, right? So as soon as D4 becomes 1, Q4 becomes 1, so Q-4 would become 0. So next cycle onwards, 0 would be fed to D1, 1, 1, 1 would be the inputs for all D1, D2, D3 and D4. Next, you have 0 coming in here and then 1, 1 would be D3 and D4. Then you have 0 coming in D3 as well and then 0 coming in D4. So here, earlier if it's a 4-bit ring counter, then it can count only till 4 values. However, if it's a 4-bit Johnson counter, it can count till 8 states. So initially we're just assuming that all the flip-flops are reset. Therefore, Q1, Q2, Q3 and Q4 are 0, 0, 0. Then Q-4, if it is fed to D1, then in the next clock pulse, your Q1 becomes 1, right? Q2, Q3 and Q4 becomes 0. So after the third clock pulse, this 1 from Q1 is transmitted to Q2 as well because D2 will become 1. And similarly, this 1 keeps on traveling till it becomes 1, 1, 1, 1. All 4 flip-flops are set. So when all 4 flip-flops are set, your D1 becomes reset. So therefore, Q1 becomes 0, Q2, Q3 and Q4 become 1. And then Q1, Q2 becomes 0. And finally, Q1, Q2, Q3 becomes 0. And then again, all flip-flops are reset. So this is how a Johnson counter works. So if we see the timing diagram, then Q1 remains set for 4 clock pulses. All the Q values remain set for 4 clock pulses. However, the setting and resetting happens after a delay of 1 clock pulse because the bit needs time for transmitting. Now, a Johnson counter would require minimum 2 logic gates irrespective of the values of n to decode the counting, and therefore they are slower than ordinary ring counter, but they are still faster than ripple counter. And Johnson counter can, if there are n flip-flops, then Johnson counters can count to 2n values. So they are more economical when compared to ordinary ring counter. However, they're still less economical when compared to Rickle counters. So if the counting value does not matter, what matters to you is the speed, then Johnson counter would be your choice. Now again, if you look at the drawbacks of ring counters, basically they come into they suffer from lockout. That is, if there is a defined unused state for a particular counter, and if the counter somehow enters that unused state, then it can never recover back to a used state. It just remains an unused state. So this can be prevented by adding a logic gate. So, if you want to make the ring counter self-starting, that is, if it enters an unused state, bring it back to a used state by using an OR gate. And that OR is receiving inputs from Q3, Q2 and Q1. So, all our inputs are all together and fed to D1. So, this is self-starting ring counter. And to prevent lockdown in 4-bit Johnson counters, just take the input of Q3 and Q4, Q-3 and Q-4 as an input to an AND gate, and then AND the values of Q-3 and Q-4 and feed it to D1, and that would solve your lockdown problem in Johnson counter. I think that's all I have to discuss about Johnson counters and ring counters as a whole. I hope you had a very fruitful session learning about this with me. I should see you soon. See you then.